Snow because a woman named Helen Snow paid for it. This is our founder, George Ellery Hale. He brought this scope up to Mount Wilson in August of 1904 from its original home at Yerkes, which was his first observatory in Wisconsin. Came up with a bunch of mules and carts on the far road. But when Hale founded Mount Wilson, he did something that had never been done, and everything he did had never been done before, but specifically in founding it, this was the first observatory ever dedicated to astrophysics as opposed to observational astronomy. So prior to Mount Wilson, they were looking through telescopes, they were drawing what they saw, they knew phases, cycles, basic stuff, but they didn't know the physics of it. Hale founded this as the world's first observatory dedicated to astrophysics. The main tool you use to do astrophysics is called a spectrograph. The job of a spectrograph is to break up what we see as white or visible light into the various wavelengths so they can be analyzed. The key component in a spectrograph is a piece of glass covered with metal, and it's called a diffraction grating. That top middle surface has scored parallel lines very, very close together, and each of those lines has an angled V groove. So the entrance to the spectrograph is a stationary slit, but you can, we'll see in a minute, but you can tilt your diffraction grating, and I'll show you an example of that shortly. So because of those angled walls, the light is going to hit it differently. You're going to see the spectrum in different ways. In addition, all 5 scopes, 3 solars and 2 night scopes, were installed with cameras for long exposures and dark rooms to develop. They used dry emulsion and glass plates at that time. This was a game changer. Hale had 3 solar scopes, 2 night scopes, all set up with spectrographs, cameras. It was doing astrophysics. All scientists came here. Consequently, truly, every significant discovery in solar, stellar, and planetary astronomy all made here at Mount Wilson during the first half of the 20th century. So this observatory is unique in every way there is to be unique, but specifically because it's where astrophysics became institutionalized. So it's all about spectroscopy, and that's true today. We see just the middle of the electromagnetic spectrum, what we call white or visible light. Spectrograph opens up the other wavelengths. Every wavelength tells you something different. So this is what spectroscopy does. Absolutely everyday science now, all research scopes go out with spectrographs and cameras, whether they're Earth or space-based. Good examples are the Hubble and the Webb. But in Hale's day, this was cutting-edge stuff. Once you start breaking up light into wavelengths, you're going to reveal the elements in and around the object. So here we have the periodic table of spectra. Every element has its own light fingerprint. These are called emission lines, and on the SNO stage, we're going to be looking at absorption lines in the solar spectrum. There are 3 types of spectra. You'll see 2 here today. You've all seen a continuous spectrum because you've seen a rainbow, but we're going to look at it with a piece of diffraction grating and talk about those angled grooves. So, when you tilt your grating, when you get to a new place where you see the spectrum differently, it's called an order. So this is first order, then they'll always be space. That's the clock driver setting. And on the ceiling, you see second order. And that's a function of those angled V grooves and the way the light is hitting them. Now, the higher your order, meaning the greater your angle is, the more spread out your spectrum will be, but that's better for getting information from the spectrograph. So for research purposes, we would always work in higher orders. This telescope has 5 orders, the 150-foot has, I think, 8, and Steve works in 7th order. The second type you'll see in the SNO stage, it's an absorption line spectrum. These dark absorption lines are formed when light goes through a cool gas cloud. In the case of the sun, the outer layer of the sun is cooler than the interior. So as the light exits the sun through that final coolest layer, the photons absorb light and the electrons get excited and they move to a higher energy level in the atom. For the emission lines, it's just the opposite. The light is going through a warm gas cloud, photons lose light, electrons drop down. So simply shown, we have the laws of the spectra stated. Here we have an emission line spectrum. These photons lost light, and so these electrons, no matter where they are going to head towards the nucleus where the lowest energy levels are. For the absorption line spectrum, it's just the opposite. Photons gain light, electrons are going to head out to the outer shell's core levels.
Turn it down a little bit.
We know the sun and all stars are made mostly of hydrogen and helium, and that's in the core of the star. As much as 95 to 98% of all stars, just hydrogen and helium. In the core of the stars where nuclear fusion occurs, which gives them their heat, brilliance, and luminosity. Once the star uses up its core elements, and that's most of the star's elements, it's going to kick out and just search for fuel. When all the fuel is gone, the star begins to die. Different types of stars die differently, but eventually dying stars will be surrounded by a cloud of gas and dust called a nebula. Inside that nebula, new stars will form. So stars have a life cycle just as things on Earth do. Different stars, different spectra. So we can look at sunspots here too if you want. Sunspots are dark spots that occur. Did you go to 150 foot?
No, we gotta call Steve or.
He's there.
He's there right now?
You can just go knock at the door after you leave here.
Oh, okay, cool.
Yeah. But anyhow, so you can see sunspots next door and they're better in that telescope. But sunspots are dark spots that come and go on the surface of the sun. Galileo knew about them as early as 1612 and was drawing them, but no one could explain why they were there, how they were different. Hale's first big discovery with this scope was in 1905. He proved that sunspots are about 4,000 degrees Fahrenheit cooler than the areas around them. He knew they occurred because of magnetic fields, could not prove it in the snow. 4 years later, in 1908, he built the 60-foot, proved that yes, indeed, sunspots are caused by magnetic fields. This went a long way towards advancing the use of a spectrograph, telescopes as cameras, and most of all, astrophysics, because suddenly, after hundreds of years, there was an explanation and proof. So what Hale did here advanced science pretty rapidly. If you photograph a sunspot and you're going to go to the green wavelength, because that's where the iron absorption lines are, you will observe what is called the Zeeman effect. The bulge tells you there is a split, a magnetic field rather, and the split tells you its strength. Now I can put a sunspot over the slit here and hook up a CCD camera and I can see the bulge, but I can't see the split. And clearly it was the same for Hale. So when he designed the 60-foot, he used a different optical system that did allow him to finish proving that there are magnetic fields. This telescope was not installed with the spectrograph in the pit as it is today. Hale got his bachelor's at MIT in physics, but he always worked at the Harvard Observatory. So when he was about 19 or 20, he designed and fabricated this. It's called a spectroheliograph. Simply described, it's an above-ground spectrograph, but it had some unique capabilities. Number one, it could isolate wavelengths. That had never been done before. So here we have a sunspot. They're never square. This is just low res. And this white stuff is called faculae. It had been observed but not necessarily measured, so Hale was able to use astrophysics to measure the temperature, and what was discovered is that faculae is a warmer area, and it always occurs around magnetic areas. So you'll see it by the sunspots, and I'm guessing there were little sunspots there because sunspots tend to occur about 40 degrees north and south of the equator. The second thing it could do, it had a little slit, and he could scan the sun and produce a full solar disk image. That had been done briefly in 1845 by a couple of French physicists using an early metal plate photographic process called the daguerreotype, but nonsense. So once again, Hale is providing spectroscopic evidence, astrophysical evidence, and most of all, photographic evidence. People got on board pretty quickly. There were some women who were really instrumental. One of them was Henrietta Swan Leavitt. She was one of the Harvard computers, meaning her job was to analyze the glass photographic plates made in the telescopes. She discovered a type of star called a Cepheid variable. Cepheid variables have a relatively short time period where they get brighter and dimmer. She analyzed that relationship, came up with a formula to measure distance. Suddenly they could measure millions of light years, not just hundreds of thousands. Scientists called her formula the yardstick to the universe. Without her work, Hubble couldn't have discovered the expansion of the universe here, so her work is very important. She worked on site here in 1925 as a scientist. I will use the word rare because it was rare for women to work here as scientists in those early days. And she proved in her dissertation that all stars are made mostly of hydrogen and helium. So I'll describe it, but then I'm going to actually trace the path of light for you by moving mirrors, and we have to reposition the telescope. But we have a series of mirrors here. So out on the far deck, we have two flat mirrors. They're called a coelostat. The bottom pivots slowly to track the top relative to the rate of rotation of the Earth by means of what we call it a clock drive, because it's very similar to a grandfather clock mechanism. There's a spinning flywheel, gravity powered by a cable and a weight, reset by the only AC motor in the system. This is run on DC. So we catch the sun in the bottom mirror, direct it to the top, so that's 1 to 2. 2 to 3 is that second top flat, sending the light down to the primary. It's a 100-foot throw. Primary has a slight concave curve. Light is focused there. You can clearly see lap 3 to 4, this beam of light with dust, and then the tilting mirror sends it through this slit. This is the entrance to the spectrograph. Before it gets to diffraction grating, it's going to travel 18 feet, and right above the diffraction grating, there is a lens, and the purpose of the lens is to collimate or properly align the light. So the light hits the grating, it's broken up into wavelengths, the absorption lines are formed, bounces off the grating, refocused by the lens, and right here, for your viewing pleasure, if you stand here and look, you'll see some wavelengths and some absorption lines. Each absorption line represents a specific element. And then we're going to go upstairs and reposition.
So is this a live spectrum of the sun?
It is absolutely live, yes.
No way. Does that change with the level of sunspot activity?
No, the solar spectrum would be changing minutely because stars age and change, but you could never see it with this telescope. But the solar spectrum is not affected by sunspots unless one passes over the
So
slit.
that's basically a constant then?
This is a constant. Sunspots are not a constant.
Right.
Yeah. Oh, you can look at sunspots on this telescope, but you'll see them much better on the 100.
Well, let's get a quick view of this one, because I told them how unique yours, you can only see yours, get ready. She's got this.
You're gonna need some welder's goggles, or you'll see white for a while. So what we're going to do, we're basically using
I
it
think
as
we're, well,
well, you might-
I like getting blinded.
Okay, now you may see smoke, no worries. This is very hot. Now, yeah, to focus the telescope, I use, I have to move the primary mirror on that carrot. It's the only axis I cannot operate
Hi, guys.
manually. It's just too heavy. So,
You
we're gonna go south. 'Cause I have
Yeah, right?
I'll be doing the end of your maintenance here, so that's not it. There is a kill switch right there, but I don't press it.
Traveling through the telescope.
There we go. Okay, I don't know what the seeing's like right now. Alright, so, that's pretty good. Alright, those are sunspots.
Sunspots?
Yeah.
I don't know if you might need
So
this
the
for
dark
your
center is
phone.
called an umbra, and around it the lighter gray is penumbra.
Yeah, these won't stay.
Sunspots occur in groups. The only way you can really know what the group is by doing the magnetic polarity readings, which Steve does daily. But I'm just guessing, this could be a group. This sunspot's probably as big or larger than the Earth. Let me know if you see smoke.
Are we there yet?
There's a live view of the sun.
I think I need to zoom in. There we go. There's a live view of the sun, guys.
Uh-oh. Did I fry my phone?
You got the sunspots there.
Did you?
No, it's back. I just fried my phone
So
there.
if you do it backwards, then you can use the.
Now, the orientation, because
The orientation is incorrect
they
for
should be
two
on-
reasons. It's flopped because of the mirrors, and also, when Steve does his drawings, you have to match what's called the P angle, and then he has to match the drift angle as well. So I would have to, little smoke, no worries.
smoke, smoke.
The paper catching on fire.
I would have to
Always
rotate this table so that
Use
we
proper
match
solar filters when
the
observing the
tilt
sun.
of the sun. But for just viewing purposes, I don't do that. Yep, okay.
That is awesome.
That's right.
Okay, shall we go up in position?
Yeah.
Yes. And I would like to give you a microphone if that's okay.
Sure.
I'm going to take his,
Okay.
and then we're just going to clip it on your,
On the lanyard, yeah.
probably the lanyard.
Okay.
It'll be fine.
Yeah, I tuck it in my shirt so I don't strangle myself.
So the main takeaway from here that most people don't capture right away, for me in particular, is this is the spot where we discovered what sunspots were. So Mount Wilson discovered the sun. And that's a big takeaway. And so just in this room alone, one of our scientists, she figured out the rotation of the sun. So the rotation of the sun, the temperature of the sunspots, the fact that magnetic fields are with sunspots, eventually learning that the sun has earthquakes, which we can't really call them earthquakes because there's no earth there. So we had to invent a whole new science called helioseismology. We take those vibrations with the towers outside, turn them into MRI scans of the inside of the sun. So pretty much everything we know about the sun was learned at this mountaintop.
It's true.
Incredible.
All right, so let's head upstairs. And the configuration of the telescope is very specific to time of year and time of day. but more time of year.
Checking audio, guys. Give me a thumbs up in chat if the mic switchover worked and you can hear things and it's not muted. Just give me a thumbs up, guys, if you can hear it
Okay.
and hear her, because I gave her a mic.
All right.
I still got the.
Okay.
Whoa, that's a trip. See through.
Yeah. This is new. You're safe. It's a cool scope. All right. Well, the first thing is when I set the scope up, this room you're in is actually a roll-off shed. So you see the crank at the end? I just hand crank the shed back to reveal the mirrors and forward to cover them in the evening. Now, this time of year, the mirrors are very close to each other because of the position of the sun and the earth relative to it. And so you can see we're starting to get some shadows. So I'm going to go ahead and move to the west. But before I do that, I have to back this second flat off because otherwise I'll hit it with the carriage on the first flat. So,
Solar telescope. The focal length of the almost looks like maybe 500 feet.
we're only about 30 feet off the ground here. So that was one of the shortcomings of this scope. The mirrors are too close to the ground and they heat up. So we're just moving this flat back so that I have room to move this one to the west. So the next step is we're going to take this flat, this first flat, back. And it has to be short movements till I clear this. And this scope is all original.
So you're moving it. Is it staying aligned to the sun?
No, I have to reposition.
Okay.
Yeah. Right now I'm just heading west because of the position of the sun. And we'll have a little shadowing for about another half hour. 12:30 to 1:30, you get unavoidable shadows, so that's probably when Hale had lunch.
So what's the resolution in arc seconds of the scope?
Don't know. Geo?
Oh, no, I've never measured it.
No.
But the whole sun is what, about 30 arc minutes? Like, just like the moon.
It would still be aperture dependent, right? So the aperture of this would be equal to that mirror, right?
Yeah,
What is the collecting mirror?
yeah.
And what's the diameter of the mirror?
This is 30 inches and that's 24 and the primary is 24.
Okay,
So now we can
20
make broader sweeps.
24 primary.
Yeah.
So you're sub-arc second precision. So you're going to definitely have a lot of detail on those
Oh yeah.
sunspots.
Yeah, and this spectrograph is a really high resolution spectrograph.
Incredible. And the focal length is just
60-foot focal length.
Okay, only 60 feet.
Yeah.
Okay.
This is among the first permanently mounted modern solar telescopes. So prior to that, you would take your telescope to an eclipse area, watch your eclipse, break it down, and take it back to your university. This has been here since, we said 1904?
1904.
And it's been here all this time, permanently mounted.
All right. That's as far as I can go safely. Oops, but I have to go a little bit more. I can't get close enough. All right. So now you can see I am just going to clear it. And it likes to take off when the mirror is off axis. So you have to just be very careful.
So is that mirror the secondary up there?
No, this is called the second flat. First
Okay.
flat, second flat. Okay, let's see if we can get away with this. So now, I'm gonna do a little positioning here.
You don't mind me asking all the questions?
Oh, no.
This is so cool.
I just,
It is cool.
I just need to do this because it won't hear you if I'm
Oh, yeah.
not next to you.
That's fine.
All
So
right,
then-
so now we're gonna take this first flat and we're gonna fill the second flat with light. There we go. All right, we're gonna have a little shadowing. Also, let me see. can sneak forward. I need a little more light down here, and that's closeness. So I'm going to sneak forward just a teens, because that's all the room I have. And let me see.
Still got a
Just on the
slight shadow, but
frame.
Yeah. Well, we can't avoid that shadow till the sun is further over. But we're full. Okay, now we're going to take this light, which is currently over here, turn around and look at the primary. We're going to fill behind us. The primary, the light is going to come in from the east. This is a real, pretty finely reduced worm gear. Takes a while.
There's the light moving up on the roof.
So we're going to have a slightly elliptical shape until the Earth moves a bit more.
So is your background in heliophysics?
No, my background's in fine arts photography and visual arts effect,
Okay.
and I taught kids science for 26 years.
Amazing.
There we go.
Look at that. That puppy is lit. Now we're gonna, and there we go.
Effectively in the air.
So the path of light is, you saw it with your own eyes, 1 to 2. And now I do need to do a quick adjustment here, and this always happens. There's a lot of,
So it stays polar aligned.
yeah, it does, but I always have to do this twice. So now look at the light again. With compound axes, you move one thing.
Light come down.
Now you're going to see the purpose of that sculpted out silver. The light is just going to slide right along.
Does,
All right.
does the silver help with the alignment?
No, it allows the light to pass.
Okay. 'Cause
The
what's-
thing I
what's
love
in
about
there?
this scope is I am maxed out. I am maxed out on every axis to get to where I need to be. And I just marvel that Hale and Ritchie had it so wired. All right, and we're good. Now, this is covered properly. This is good, we're good.
It's awesome. I love it.
It is a cool scope. I love it too.
Yeah, it beats our PSTs.
So
This
would you
is-
be okay if they step on?
Absolutely, yeah.
Especially Nate, because I know he loves heights.
Yeah. This
So
is
if
the,
you go all the way around and come over here, you'll be able to see the governor that's spinning and moving.
the flywheel, yeah.
There's our view, by the way, guys.
Yeah. So this is the world's
Up over
oldest
LA.
permanently installed working
Get some
solar
mountaintops.
telescope open to the public. I
Right.
open to the public every weekend.
Up on Mount
There's
Wilson.
one 4 years older
Okay,
in
so we
India
step
at
over this.
Kodaikanal. And I discovered one at the University of Japan in Kyoto. I know nothing more about it than that
I
it's
know.
green.
So
And-
what's the one at Kip Peak?
I don't know. It's not horizontal, is it?
It seems like go down a mountain.
Oh, there we go.
Yeah.
It sort of runs
Wow.
up the hill.
Yeah, I do not know. I don't know if it's a horizontal configuration.
That's the governor.
Yeah.
Yep.
So that's the flywheel. It's just this beautiful brass
That's fly-
flywheel. We
it's
actually
brass
just adjusted the
flywheel.
tracking.
Okay.
Yeah.
Thanks, Gio.
So this telescope
Man.
is now tracking
know if
really
I can-
well. But you can see, Gio, I am
You guys
maxed
see the
out.
brass in there? It's a little.
And in fact, I look how close I am to this. I'm not sure if I hit this if I would be electrocuted, but
You got about what, maybe
It looks a little sketch.
an hour more of viewing that you can do before the sun gets in a horrible position.
I'm
with the tree
good till about 3:30, and then that tree.
That tree gets
So
in the way.
there's talk of taking it down. I would
So
like to
guys,
see
look.
it go because it cuts about 2
It's the
hours of
snow
light out.
solar telescope at Mount Wilson.
I like it,
We're touching it. I'm touching it.
but I love it when it's maxed out like this. It just makes me chuckle.
Hey, we can see people.
I know.
now with you being fine arts
So cool.
photography and
Mm-hmm.
being in this realm, have you toyed with daguerreotypes at all?
No, I haven't.
Beautiful.
You haven't? 'Cause
No.
You can get because they
We got John here from
Crazy.
Learn to Stargaze. What do you think, John?
Absolutely nuts.
Yeah.
Is this
I do
cool?
like a lot of help.
We are.
Yeah.
We're really high.
What
Yeah.
we did do a couple,
We're up
probably as much as
Snowcat
3 or 4
Mountain.
years
You guys
ago,
see
in the
it?
60-inch,
Okay.
we got some glass plates,
SunshineNate
and so we
here.
put them in the holder and we photographed
We're
the
having
moon
That's awesome.
And then
love
we went
space stuff,
downstairs in the
guys.
dark room and used the old
We
automatic
love telescope
agitators.
stuff.
It
This is
was
snow
an homage
telescope.
to Hale, but everyone was so excited. It was
On Mount
amazing.
Wilson, and I don't know. That's the 100-footer.
Yeah.
I think we're going to that next. If you guys want us to stay
It's a killer
on,
scope.
the Wi-Fi cuts out between facilities. I can try to like keep it on as long as it's within a minute or so I get over there, so the live will like just like pause or freeze, and then we'll be over at this one.
But I mean, it just cracks me up how it's just so perfectly designed.
Yeah,
Yeah.
that's, I mean,
how
the
did
things
you-
that boredom create.
How did you word
Like,
that?
the mic out. Because her talking was probably getting over mine. I always forget that when the mics are in. Check out these mountains over here. Really pretty view over there.
I'm gonna come inside.
Yeah. I emailed Cody Canal, it came back from the purple, but I don't know.
Would that light fry a burger?
This may be the only place in the whole world where just anyone can walk in and see
That's a
it.
great question. Has anyone ever fried a hamburger at the focal point?
Well, not at the focal point, but I did warm up some Starbucks. A pastry the other day, and it took about a minute on each side.
So there's your answer.
If we get to X amount of likes, we'll bring back some marshmallows next visit.
I'm pretty sure I could fry an egg.
Yeah, probably.
Yeah.
I think, Nate, that could be your viral YouTube video of the.
Or you could take a cast iron and probably get it warm
Yeah.
enough in time.
Yeah,
For
it's
sure.
really hot. I mean, you
Yeah.
saw how the Great Card
Yeah.
smokes, so there's plenty
Yeah,
of
so
heat.
that's
Yeah,
451, right?
yeah.
Yeah.
Catch fire on.
It's a solar telescope on Mount Wilson in California.
Solar telescope. Mount.
We're at the Mount Wilson Observatory learning a little bit about the telescopes here. Giovanni, what's your name again?
Patricia Hill.
Patricia Hill.
Patricia Hill.
Patricia Hill here.
Sunspots were.
And Telescope Man is at telescope_man. I'll be linking his channels in all these lives.
Do you have a social presence? A social media presence?
I do. Odie is on Instagram.
Oh,
You can follow Odie.
Odie, who hasn't woken up yet.
We're gonna follow the dog. Have you guys seen Odie?
Odie Maurice.
Odie Maurice.
He's much more interesting than I am.
Odie Maurice on Instagram.
Far more than one.
If I stand here too long, my head starts to warm up.
Yeah.
That is cool. So as we go forward, it's gonna get more and more concentrated.
Right, here's Odie, guys.
he's dreaming.
Frankenstein switch, did you hear it?
Oh.
Just about at the point where you're just at the exit.
Stick your hand in there.
What's he doing up there?
The switches are flicking by like solenoids.
Yeah, those are DC relays, and we often have to fuss with them. This telescope wasn't used very much at all, and then 7 years ago when I started operating it, I quickly decided, oh my God, everyone needs to see this. So they pretty much just gave it to me. So I've curated it, the photos, the mini museum. We painted the top stuff during the pandemic. So it's now just in really good order. I maintain it, I oil it, I clean it, and I listen. So when I hear, oh yeah, I used to work in machine shop and on an airship, lots of stuff. But when I hear certain sounds, it's like, okay, keep listening. Other sounds, uh-oh, call Rob. Other sounds, power down. So in a big system, you're always listening.
Just on an airship.
I did.
That's so cool. You're pretty much the coolest person I've met.
All right, Zach, can you hold YouTube?
Yeah.
Yeah,
This is-
it's a fun.
We're using phone mic.
Now, Odie Maurice has
Open it
grown
up.
up on this mountain. He is about to be 7 in February, X about 10. And
we gotta say hi.
He's allowed to go to sessions in the 60-inch, but he can't go to the 100-inch because it's dangerous.
Yeah.
He's a really good, he's a good telescope dog because he's so chill.
He's the only one with a badge, and out of all the pets that come up here, I think he's the only one that has an actual dolphin badge.
He has 4 badges. Of
Oh.
course, I make the badges. He is STEM support. We have a summer astrophysics institute called SOAR. He's SOAR support. He is a generic volunteer, and he truly is a telescope assistant. Yep. He's a
Ours is a golden retriever at our observatory in Stella.
So there was a Stella here, she was wonderful, that scientist moved away.
Yeah.
Stella used to dash into the snow when he was a puppy and they played. I miss
Was he?
Stella terribly.
Oh,
Is he a mix or is he a full bull terrier?
No, he's a full bull terrier,
Yeah.
he's just extra big.
Yeah.
And then he used to have one ear that stood up, but it flopped.
well, maybe I'll,
He's so sweet.
my wife wants to move back to California, so maybe we'll be here soon.
Anytime I'm here.
Oh.
You think Steve's still over there? It's
I know
1:40.
he's still over there,
Yeah.
because he's waiting for the tour.
Oh, okay, I'll go knock
Cool.
on the door right now.
Oh, we might interrupt another tour.
Thank you so much.
You're welcome, my pleasure, thank you for coming.
Grab the
Yeah, John.
Oh, this John.
microphone.
You can find me on YouTube with an excruciating 2-hour tour of the observatory.
Awesome.
I was able to watch myself for 5 minutes. Is enough. But he says he'll see you out.
Aw, thanks, baby.
He's a little Geo. He loves Geo. So here, let's put the telescope up.
Yep. Yeah, so I'm learning to stargaze. IT and TikTok and
Oh yeah.
everything, and
Yeah.
so I'm the director of the Abbey Ridge Observatory
Oh, you are.
in Canada. So it used to be Dave Lane.
Uh-huh.
He passed away.
Oh,
So this was the observatory that, it was the first remote observatory that was open to the public for free. So anyone could go on Facebook,
yeah.
and the observatory's computer would read the Facebook messages, add the observations to the queue,
Oh,
and do
that's
it. So
very
even exoplanet transit observations, it could do over Facebook.
Wow.
And he was just completely dedicated to having that open to the public, so it would be free,
Mhm.
and you could make your own HR diagrams with it.
Oh, that's
And
wonderful.
so now we've got a technician working on it almost full time, and so hopefully he'll have it back up and running soon.
It's so important to provide access. One of my greatest mentors is a man named Mike Simmons. He founded Astronomers
Oh, I
Without
know Mike.
Borders, and now he has
Yeah.
equity in astronomy. He's taking
Nate,
telescopes to
do you wanna
refugee camps
Kill this or you want this in?
the Ukraine. I mean, he's doing serious
No.
outreach. Right now, he's in Palestine. Yeah, he's a cool
I didn't realize he traveled like that.
He travels to war zones and he
Yeah.
takes scopes and science to kids who are barely hanging on. He's really amazing. So he's the one that really championed me to have this be my telescope. No one else wanted it.
We wrote a book for Mike, so we had a book
Ah,
that I produced called 50 Things to See with a Telescope, a Young Stargazer's Guide.
uh-huh,
And when he did the One Sky telescope,
yeah.
we actually produced a book to go with the telescope.
Yeah, then you know Mike's a good guy.
Yeah.
Yeah, so that was, Tom Guinea, our director of telescopes, was my other big mentor. And I learned from people like Gio. Gio's amazing. Gio is great.
This is what I'm looking at up here, 22. I need to grab
He rarely comes up.
battery pack
Yeah.
out of the trunk.
He, I haven't.
Of the
we
car.
put it together once, so I just have one.
Yeah, we can put this in there.
He's
And
just
then,
really busy. He approached me to write, like, lessons.
I need the little black USB regular to USB-C and then just one of the black.
All right, well, thanks for letting us
You're
crack the
welcome, you guys. Bye, Gio. Absolutely my pleasure.
Thank you so much, that was awesome.
Party. You gonna come to the holiday party?
I am, but I won't be wearing a silly sweater.
I might wear a silly
You're
vest.
most welcome.
So I was able to share that with 400 people.
All right, guys,
Saw your whole talk, and with him.
where are we going now?
We're gonna go to the 150-foot solar tower.
150-foot solar tower.
So the snow telescope discovered that the sunspots were colder regions on the sun, but it was 150 foot in the 60s.